All right, so let's take some time and talk about composition of substances and solutions. Yeah, a lot of this is going to be just a little bit of a formalization of what we've talked about and done either previously within the semester or within the laboratory setting as well. And just to touch on a few things. Again, our molar mass. Mass of 1 mole of a substance. And as you know, calculated from the periodic table. And the last thing that I want to say with regards to that is keep 2 decimal places. Calculate the molar mass for malachite. And malachite is a relatively complex compound mineral. Now let's see here, what do we got? Cu2, OH twice, CO3. When you are asked specifically to determine a molar mass as a question, as a calculation question, I do want to see your setup. So don't just toss down the numbers or just toss down your answer. I know that many of you can do it that way. Just please don't. So I've got 2 coppers, 5, whoops, let's try that again. For oxygens, I've got 5 of them. 2 with the 2 hydroxides, and then 3 more in the carbonate. Hydrogens, 2, and carbons, just 1. So that's 63.55. That's 16.00. That's 1.01, and that is 12.01. Let's see. Now at this point in time, once you have that set up, I'm okay if you don't want to write down the 2 times 63.55 equals, right, 127.1, or that, 10, or that 16 times 5 is 80. Or that this is 2.02, or this is 12.01. That's fine. I don't have to see that part. I want to see, though, at least your setup. 127.1, whoops, and 80, and 202, and 12.01, and it's 2 to 1.13 grams/mole, and don't abbreviate with MO, or just don't abbreviate with just M. It's either MOL or MOLE. Sorry, I just the little M doesn't work. Get used to also Cu2, OH, 2, CO3. Get used to writing the compounds all the way out. One of the biggest uses for the molar mass, of course, relates mass and moles of a single species. Be it an atom, a molecule, a formula unit, it does not matter. But it has to be a single type of stuff. So mass and moles go through this molar mass. This means we can ask questions such as, how many moles of NaCl are in 5.84 grams of NaCl, question mark. One of the things that I like to do is I like to include with questions like this, I actually like to include the molar mass, 58.44 grams/moles. And the reason why I like to include that piece of information is it is a separate skill that I would be interested in testing or assessing when I ask for calculate the molar mass for malachite. Here, with this question, how many moles of NaCl are in 5.84 grams of NaCl? I'm not looking for your ability to calculate the molar mass. One of the things that tends to happen is I tend to use one chemical formula and then ask a set of questions about that chemical equation, and then ask a set of questions about that chemical equation. Well, if you mess up someplace, like, I don't know, maybe with the molar mass, guess what? Your answer is going to be different. Not necessarily wrong, but different. If you incorrectly calculate your molar mass, but you use that value correctly, then you know what you're doing for the second part, and I can't really knock you points for the second part. That's why I like to try to separate some of these things out. So how many mole NaCl are in 58.4, whoops, let's try that again. 5.84 grams NaCl. Remember, with our molar mass, it's 1 mole of whatever NaCl is equivalent to some number of grams. So 1 mole of NaCl is 58.44 grams. I need 58.44 grams, and I have 1 mole of NaCl. So 5.84 divided by 58.44, boom. And I end up with 0.0999316. And so I will round that to 3 significant figures, 0.100 mole NaCl. So I can go, in this case, this question was moles to mass, or I'm sorry, let's try that again. Ugh. So this was how many moles? So this was from a mass to moles. I guess we could call it that kind of conversion. We can do the flip side as well. Now this mass to moles is something that you did quite a few times. Within the laboratory setting. You weighed out this many grams of, or you weighed this many grams of copper 2 sulfate. And then the question was, hey, how many moles is that? Because we were trying to find the water of hydration. We're trying to find that mole to mole ratio between the two. Another type of conversion is just the reverse of this, and that's to go from moles to mass. And that would look something like this. how many grams of CO2, 44.01 grams slash mole, contain 3.2 moles of CO2? Question mark. Another thing I would like to be pointing out is I want you to look at how many moles of are in. Notice particularly this question involves NaCl and NaCl. This second example, how many grams of, so how many grams of CO2 contain 3.2 moles of CO2? Once again, CO2 and CO2. The other piece in this expression has units gram slash mole. Sometimes you'll see it addressed as the formula weight. Formula weight, atomic weight, molecular weight, all refer to the mass of one unit. And it has, and we use atomic mass units for that. Number-wise, it's exactly the same. So if I say the formula weight of carbon dioxide is 44.01 AMUs. Scary as heck, right? Not so much. It means that one molecule of CO2 has a mass of 44.01 atomic mass units. 1 mole of CO2 has a mass of 44.01 grams. Numerically, they're the same. Unit-wise, we're talking either about a single formula unit or a box, a mole of formula units. Getting back to this question here, how many grams of CO2 equal out to that 3.2 mole of CO2? And yes, I know it's a pain. It's a pain to keep writing out CO2 or whatever it is. Do it. Do it, do it, do it, do it. At the very minimum, with the molar mass, 1 mole CO2, 44.01 grams. As soon as we bring in chemical reactions, then we're going to have an issue. Plugging and chugging, I end up with 140.832 grams, making it look pretty. 140 grams. Okay. What is a mole? And the way to think about a mole and a molar mass is it's a way to count a bunch of individual pieces by using its weight. Now, the fancy definition is given in the text. 1 mole of anything is defined as 6.02 times 10 to the 23rd power particles, pieces, parts of anything. So 1 mole of helium, well, that's the same as saying I have 6.02 times 10 to the 23rd power helium atoms. One mole of sodium chloride, NaCl, there's 6.02 times 10 to the 23rd power NaCl formula units. So if we put it together, we can, if we'd like, think about how if I mass out or weigh out, um, 5.84 grams of NaCl. According to that calculation, that is 0.1. At 0.1 moles of NaCl. Well, that's nice. Or, if you want to look at it another way, I have 6.02 times 10 to the 22nd power. Individual formula units of NaCl. Again, formula unit, it's kind of like a molecule for ionic compounds. You can go for that. Why do I want to worry about doing something like this statement? Why do I want to look at this idea of having this relationship between what I mass out, what I weigh out, and this number of particles. Chemical reactions occur when individual reacting species collide. In other words, chemical reactions happen on the atomic, the molecular scale. I have to be able to go from macroscopic to the submicroscopic to the atomic level. But I can't unless I have some kind of intermediary that says, oh, if I weigh this much out, I have this many individual pieces. Because now, if I know how many individual pieces, then I can go back and figure out, oh, how much mass. The mole lets me go, lets me think about what I can do in the laboratory. And it relates it down to how many individual pieces or parts I have. And writing out exponents, 6.02 times 10 to the 22nd power, is not a lot of fun. Putting down a 602 followed by 21 zeros, or in this case, it's not fun. So we need to have then another unit to describe a bunch of individual little pieces. That's what the mole does. The mole describes the number of, it holds into it the number of individual pieces. And some questions are just better off asked about how many boxes rather than looking at how many individual pieces. Now, another way to look at this is we often talk about a mole is a chemist's dozen. That's actually not what I want to say. That was a different tangent, sorry. Okay, now let's do this. Suppose we look at H2 plus I2 goes to make 2HI. It's a one-to-one relationship. So one molecule of H2 reacts with, oops, one molecule of H2 reacts with one molecule of I2. 10 molecules. H2 reacts with 10 molecules of I2. Twelve molecules H2, right? 12 molecules I2. What is the relationship on either side of the ratio symbol of the colon? They're the same. It's 1 to 1. So instead of talking about these little things, again, chemical reactions occur when individual reacting species collide. So one molecule H2 reacts with one I2. 10 molecules of H2 would need 10 molecules of I2. 6.02 times 10 to the 23rd power molecules of H2 would need 6.02 times 10 to the 23rd power molecules of I2. So we can then, instead of writing out how many individual pieces, we could say, 1 mole of H2 is related to 1 mole of I2. So our mole ratio is going to let us look at a relationship between any two pieces, any two different things. I almost want to write down things. I'll put down species. So a mole ratio lets us compare two different things. Let's take sucrose. Should I do sucrose? No. How about, what do I want to do? I'll do carbon dioxide. So CO2. If we go back to, well, how do you calculate the molar mass of carbon dioxide? You said, oh, yeah, I've got carbon, and I've got oxygen. I've got 1 carbon, and I've got 2 oxygens times 12.01 times 16, blah, 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 blah. This time I want to focus more on the 1 and the 2. 1 carbon dioxide molecule contains 1 carbon atom and 2 oxygen atoms. Okay. Could I also say if I have 20 carbon dioxide molecules? And I could somehow split them apart? Well, that would be 20 carbon atoms and 40 oxygen atoms. If I had 1 mole of CO2, contains 1 mole of carbon and 2 moles of oxygen. In this case, my different species are the various elements within a single compound. Chemical formulas are built on whole number mole ratios. We had the lab in which we compared empirical and molecular chemical formulas. An empirical formula is the simplest whole number ratio of elements in the compound. The actual chemical formula, or maybe the molecular, is the actual whole number ratio of elements in the compound. The molecular formula is going to be a whole number multiple of the empirical formula. So the empirical formula can be the same as the molecular formula. In that case, the whole number is 1. If you take a ratio of the molar mass of the actual compound and divide it by the molar mass of the empirical compound, you will get that multiplier. So for example, has a molar mass of about 78 grams per mole, and an empirical formula of CH. What is the chemical formula of the compound? Let's see, I know that the empirical mass, I know I can find the empirical mass. I have my empirical formula. So I know my empirical information. I have CH. I know that carbon is 12.01. And I know that hydrogen is 1.01. So my empirical molar mass is going to be what, 13.02 grams/mole. And then I know my actual, so I know my molecule molar mass is 78. So 78 grams per mole over 13, and we'll just call it 13 grams per mole equals 6. So my actual compound has 6 of the CH units. C6H6. How do I find an empirical formula? Question mark, question mark. Okay. Now we did it a couple of ways. ultimately what you need to have is you need to have masses of the components in the compound that you can change into moles. Sometimes you are given what's called a percent composition. A percent composition is, well, it's exactly that. It's a composition by percent. It doesn't help much. I know it doesn't help much. So percent composition by mass. Whenever you have a percent composition, it's always part divided by the whole. So a mass percent is going to be mass of the part divided by mass of the whole times 100. So if I tell you, for example, a compound is 82.27% nitrogen and 17.76% oxygen, squeeze, by mass. What is the empirical formula? I'm sorry, that's not oxygen. Oh my goodness. Let's try that again. That would be hydrogen. That would have been really bad. What is the empirical formula of the compound? Question mark. All right. If you're given a percentage, make the assumption that you have 100 grams. So my first step to determining my empirical formula is to figure out the mass of each component. So I'm looking for the mass of N and of H. Again, I'm going to assume 100 grams of sample. If I assume that I have 100 grams of sample, then I would have 100 grams of the whole thing times my percentage. So I'd have, so so if I have 100 grams of sample, then you would have 82.27 grams of that 100 is nitrogen, and .76 grams is hydrogen. Really, all I did was take 100 times 0.8227. That's really all I did. Second piece. Determine moles of N and of H. So I've got two parallel calculations. One is going to be how many moles of N are equal to 82.27 grams of nitrogen. And then the next calculation would be how many moles of H are equal to 17.76 grams. Come here. Of H. According to my handy dandy periodic table, I have 1 mole of nitrogen for every 14.01 grams. And for every 1 mole of hydrogen, that's 1.01 grams. So now I can just do my division. And 82.27 divided by 14.01 equals 8. Whoops, let's try that again. 5.87223 moles of N. And here I have, well, 17.76 divided by 1.01. It's pretty dang close to the same thing. Let's try 17.58416 moles of H. Okie dokie, piece 3. Determine the whole number ratio. So as of right now, I have nitrogen 5.87 and hydrogen 17.58. Ugly. I'm going to divide by the smaller. So 5.87, 5.87. Okay, so N1H 1758 5.87, boom, 2.995. NH3.